Hiya, me again. Okay, yay, we're actually going to finally do the real calculus-y stuff. Okay, first a little review of slope. Okay, so slope is M, because M stands for slope. Okay, and for us it's rise over run, which literally means the rise over the run, okay, which is the change in y, the up and down, the rise on the Cartesian coordinate system, divided by the change in x. Okay. The Greek word for change is delta. So delta y over delta x. The Greek symbol for delta is a triangle. Okay? And sometimes people just use dy dx. Because that's a little easier, like especially if you're typing in Word than making a triangle or whatever. Okay? So these are all the same thing. It's all slope. So if I have, say I have 2 points. Say I have 1, 4 and 3, 8. Okay, if I were to plot those 2 points, 1, 2, 3, 4, 5. Okay, so from the origin, 1, 4 would be here. Okay, and 3, 8. 1, 2, 3, and 8. Okay, so the slope tells me how steep that line is. So for us, mathematically, it's y sub 2 minus y sub 1 over x sub 2 minus x sub 1. You did this in algebra. Keep saying that. Okay, now remember these are subscripts. They don't have any mathematical property. They're just showing that this is the y value from point 2 and this is the y value from point 1. Same with the x's. It never, ever, ever, ever matters which is point 1 and which is point 2. But you need to be consistent within your problem. I go in order because I think that's easy. So if I call this point 1 and I call this point 2. Okay, what is my y sub 2? It's the y value of point 2. What is my y sub 1? Well, that's the y value of point 1. X sub 2, x value of point 2, minus x sub 1. Okay, so that gives me 4 divided by 2 is 2. So that gives me a slope of 2. Remember that? Hopefully a little bit you remember that. Okay. Now, calculus is a study of the rate of change. Okay. Let's suppose I have f of x equals x squared, and okay, we'll just call it that, okay, which is just a basic parabolic function. I just wanted to say parabolic real bad. I'm trying to get my straight edge here. Okay, so if I were to graph this, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Alright. So when x is 0, 0 squared is 0. When it's 1, it's 1. When it's 2, it's 4. 3, it's 9. And then same deal on this side, because you would be using parentheses for the negative 1 squared would be negative 1 times negative 1. Okay, and then this would keep on going. Okay. Now, most things in real life are nonlinear. Okay, which means that they're to some other power than just a 1. So a curve. Okay. Now, if I look at the slope between, say, this point and this point, that's going to give me an average rate of change from when x is 0 to when x is 3. Average rate of change is helpful in certain circumstances, but not that much in others. For instance, if it took you an hour to go 60 miles, your average rate of speed was 60 miles an hour. You weren't going 60 miles an hour pulling out of your driveway. You weren't going 60 miles an hour in the turnpike. You were going 85. Okay. Now, what the cop who's trying to catch you speeding cares about, not your overall average rate of speed. He cares about how fast you're going when you go past his radar gun. That's your instantaneous rate of change. Okay, so while this slope is a little helpful, it doesn't exactly give me a real accurate picture of what goes on with my function. How rapidly is it changing between, say, when x is 0 and x is 1? All right, so let's say, I'm going to make this bigger. I'm just going to make that one part. Let's just do this portion over here. 0, 1, 4, 3, 9. Oh, Beth, you suck. Okay. Pretend like that's beautiful. Let's try that again. Okay. Now, we can tell from any point on our curve here, okay? If I say this value is, and remember y equals f of x. Okay, so this point here, if this is x, okay, then this point is x, f of x, right? And if I say the distance between here and here, even though, the way I have it drawn, it's obviously a 1. Let's say it's h. Okay? So then this point would be x plus however big h is. So that's x plus h is the x value here. Okay, so that's x plus h. And then the value on this side is f at x plus h. Right? Okay? So, for instance, if this is 1, and this space is a 1, then this is 1 plus 1, that would be 2. And the y value would be f at 2. 2 squared is 4. Okay? So just instead of using numbers, I'm throwing that h in there. There's a reason. Okay. So now, if I get the slope from here to here, okay? And we'll just say, for the sake of argument, this is 0.1. And this is 0.2. So our slope would be y sub 2 minus y sub 1 over x sub 2 minus x sub 1, which I could reduce. These x's are going to cancel. So the slope would be this. Okay? Following with me? Okay, now, what happens when h gets smaller? Suppose now I go from this point to this point. Okay? I made h really little. Now make this h. So now it'll be this will be 0.2. Okay, so now I'm getting closer and closer to actually showing the rate of change down here. This gives me that average, and this is still an average rate of change, but it's a little more on the mark. Well, what happens as h goes to 0? The limit, okay? So when h gets smaller, until, so you have this point and this point, okay? And the distance between the two is h. Well, if h gets smaller and you keep bringing this in, okay, now your slope starts to be more and more identical to what's actually occurring with the curve. So what happens is h gets almost to 0, to where these points are just touching each other. That gives you your instantaneous rate of change. But if I take the limit as h goes to 0, you're going to have division by 0. Undefined, right? So, now let's take a look at this x squared thing.